Hi, ET350. This is lecture 7. Today we're going to go over a DC generator example. We're going to look at a series DC motor example, and then we'll look at a shunt or parallel wound DC motor. Okay, so let's look at this simple example. I believe this is a homework problem, but I felt it was good to go over it. So what we have here is your external magnets. They could be electromagnets or permanent magnets, and it's creating a magnetic field going from north to south. That's one of the 7 fundamentals. And if you look closely, what you see is the commutator and the brushes. And this commutator is attached to these wires. This is actually a design that you guys could do for your DC motors. And so you can imagine, for example, if you had this commutator here, I'm going to try to draw an isometric view. Like this. Okay, so you can see that we have, what do we have? A, B, C on the bottom, and D. And look how A is oriented, or this wire. A is going through here and then coming back. Oh, sorry. A is coming this way and then coming back through the B. So it's going around like this, around the back, and then coming up to the front like this. Or this D wire, so this is A and A, this D wire is emanating from the A terminal and coming this way around and then back through here. Okay, so I hope that makes sense for all this. So the magnetic field is now going like that. Okay, so this is an ISO view of the same thing. Now this thing can turn, the commutator and the armature turn together, so they're fixed relative to each other, and then the brushes stay fixed relative to the stator, so they don't spin, these two brushes, right? And so you have a contactor here, and so I have this V, and imagine this V as like a measurement. I am measuring with the red lead at this positive and the black lead at this negative. I'm measuring what is the sign, SIGN, of the voltage induced if I were to rotate, force this thing to rotate counterclockwise, okay? And so what we can do is we can use our fundamentals, our Faraday's law, or Bill's law, and see which way the current is induced, okay? So I have this next figure here, and so this is just the same thing redrawn, but let's see what's going on. In all these coils here, you can imagine if I'm rotating it, some external prime mover is rotating counterclockwise, there's going to be a force always in the opposite direction of rotation, always opposing. And the reason why it's opposing due to the Faraday's law, Lenz's law, physical nature of the device. You can see that the B is drawn from north to south. And then what we can do is we can say, okay, we're going to have a force opposed. That's due to Lenz's law, Faraday's law. But then the current that supports this force opposed is from Bill's law. We do the same kind of analysis when we go the current that's supporting the B opposed from Ampere's law, but it's the same thing, right? And so what we can do is we can pull out our cube and we can say, well, let's say we don't know which way the direction of current is. To get current in here that's going to support this F opposed, we can take this cube and go, well, if F has to be in this downward direction and B has to be to the left, you can see that B to the left, then we can say, well, then that current must be pointing up towards us, and that's why we have a dot. Same with on this side. If we have a F opposed that's kind of downwards and a B that's going to the left, the I is going to go up. It's going to be the opposite that's true on this side. So on this side, B is still going left, but now the F is right here going up. So now we got F going this way, B going that way, and I is now going in the page, and same with over here. Okay. So that's nice. And now we can follow the trace of where current would go. So if current is going into the page, if I follow this A, imagine positive charge flow is going in and then it's coming out. Where is it coming out? It's coming out over here, okay? And building up positive charge on this side. All right, good, that's for this line. What about this one? If current's going up, it's building positive charge on this terminal and then leaving and going this way, right? Okay, good. What about over here? We can see that if all the, in other words, wherever you see an X, you're going to see negative charge build up over here, right? And then here you're going to see positive charge build up. That's essentially what's going on because these dots are going to have positive charge coming and building up here. So that means a positive charge is going to build up on this B terminal and a negative charge is going to build up on this D part of the commutator. Since the brushes at this moment of time are touching on the right side, the B terminal, and the left side touching the D terminal, you're going to build up a positive charge on this side. If I were to measure this voltage with the red lead over here, what you're going to see is that you're going to read a positive number. And so let's just repeat what's happening is you are spinning this in a counterclockwise fashion. At this moment in time, the forces are going to always oppose, and the currents are going to be induced in such a way to help generate that force oppose. The force oppose is from essentially Faraday's law, Lenz's law, and I should even write that down. So the force oppose is due to Lenz's law, okay? Lenz's law, right? That's the negative sign in your Faraday's law. And then the current is supporting the F oppose to fight that rotation, okay? And so what you should see at this moment in time, a positive V induced if you're measuring it like this. Of course, if I flip the leads and I measured positive over here, negative here, this would switch, but I think you guys get the gist of what's going on. All right, good. Okay, let's go run through a numerical example of a series DC motor, and I hope it ties in some of the fundamentals again. And remember, a series DC motor, what equation do we have? We have the Bill's law / Lorentz force, same thing. We have torque equals K phi IA. We have the Faraday's law, this is torque developed, EA equals K phi omega M. And we have the Ampere's law, phi equals KF IA, because it's in series, so therefore the IF equals IA, right? These get substituted in, so you get KKF IA squared, and you get KKF IA omega M. So these are your series motors. Now, these two equations are valid for any separately excited series, shunt, permanent magnet, doesn't matter. These always are the case. But due to the intricacy of the circuit, then you can get these little add-ons here with the Ampere's law. We'll see the same thing when we look at shunt and parallel wound later in this lecture. So let's keep going forward. In this problem, they give us two cases where you're running in a case 1 situation, a case 2 situation, and they ask, what is the speed in this case 2 situation? So if we look at both of these situations and we look at the numbers that they give us, they do tell us the speed of the first situation. They tell us the voltage, and if you look at the voltage, it looks like the voltage is the same. So you're applying the same input voltage as a motor, but it looks like you're probably going to have a different speed, and the reason why is you're having a different current. Look how much more current you have in this first case than the second case. Don't forget that the torque speed curve for a series motor looks like this, right? It's still the same idea, low speed, high torque, high speed, low torque. And so remember, torque is proportional to current. So if I see more current, I probably have more torque. So let's say I'm here for case 1, right? If I go over here, I see I have less current, which means less torque. So what I'm thinking is we'll probably be over here for case 2. So I'm imagining torque developed 2 is less than torque developed 1, right? I'm sure this is going to produce a smaller torque than this by this equation. And I would imagine omega M2 is the opposite, is greater than omega M1. So what we're expecting is that this number is a bigger number than this one. Okay, so I hope this all makes physical sense when we find the numbers, right? Because what we want to do is we want to calculate the numbers, but we don't want to lose intuition. Okay, I have written here basically what I just stated. Here's an assumption. We're going to assume that the resistance doesn't change, RA and RF doesn't change, and K and KF don't change. So those are the motor constants. Okay, so we'll keep those the same. Let's see what we can do. Now, remember, we want to solve for omega M2. And we have this nice equation with Faraday's law, right? So EA2 equals KKF IA2 omega M2. And if we look at what information we have, we know IA2, that's 10 amps, but we don't know EA2 and we don't know KKF. We do, however, know the resistance and we know the input voltage and we know the current. So we can get this EA2 probably from our circuit analysis, our Nodal Ohms law. right? And remember, for a series motor, the field coils and the armature in series. So you have VS, RF, RA, and EA. You can easily write your Nodal Ohms law like this, okay? And if I look at this one, I could solve for this EA2 because I know VS, IA2, RF, and RA. Okay, so just using some algebra, bring the RF and RA over, and then punch in the numbers, I get 275 volts for this back EMF in this case. If you look at this back EMF goes, well, this number is actually pretty close to 280. It's smaller, so that's good. So that means current can flow left to right here. But yeah, so that's just another check. If you got an EA that's bigger than the source voltage and it's still running it as a, or it's stating that it's running as a motor, maybe you got some calculations wrong, or maybe the problem is stated incorrectly. Okay, so that's just a little intuitive check. Okay, so I have this voltage here, and then I have this current here, and I'm still looking for this omega M2. So the question is, how can we get this KKF? Because we can get that KKF, and maybe from case one, we can essentially plug this in and solve for omega M2. If we look at over here, we can probably get KKF using, again, our equations, right? Remember, this is KKF here, right? So if we go to case one, we can look at these equations and go, well, could we get any of this information? Could we get EA1? We probably could play the same game and do the whole Nodal Ohms law, probably. Can we get IA1? I think we can because we already have it. They're giving it to us. Can we get omega M1? We can. Good. So we can play the same game as here and use the Nodal Ohms law, get the EA1, and then solve for omega M, or sorry, KKF, right? So if I look over here, we write that down. We write the same Nodal Ohms law, and then we plug it in, and let's see what we get. So we can see with these two equations, two unknowns, right? Then we just crunch and solve for this KKF term, right? And let me just do this a little bit slowly. EA equals KKF IA1 omega M1, good. IA1 equals VS minus EA1 over RF plus RA, good. These are all two known things. I can bring this RF plus RA over to this side, good. And I can solve for this EA1, good, by bringing, kind of swapping these things, good. And then finally I say, well, this whole thing is equal to this guy, good. And now I have one equation, one unknown. I just bring this KKF, I bring this IA1 omega M1 over to the other side, and I can solve for KKF, fantastic. I just plug in the numbers, okay? Now, before I plug in the numbers, I do have to solve for the omega M1. They do give me that number in RPM. Remember our trick, if I just block out the digit over here, it's gonna be about 120 radians per second. The factor is 6.28 over 60, right? 6.28 over 60, about 1/10. Yep, 125 radians per second. Okay, this is 280. This is 25 now. This is 0.2 plus 0.3, 25, and 125.6 radians. Punch that into the calculator, and I get 0.085. And notice the units, Webers per amp, right? And you might go, why is it Webers per amp? Well, you could do the dimensional analysis, and I'll save it as a exercise to viewer to figure out why that that is true. Okay, all right. Oh, I have it written here. Oh, guys are lucky. It's because K is unitless and KF is from Ampere's law, Webers per amp. Okay, all right. Past self is being nice. Okay, so once I have KKF, I come back, plug it into that equation, solve for omega M2, and we are set. Not too bad, right? And you can see that's what I'm doing here. 275 was the EA in the second case, 0.085 and 10, right? Okay, and I get 323.5 radians per second. Does that agree with our intuition here? We calculate 125 for omega M1, and now we're getting 323.5. Yay, that is good. That is consistent with our intuition that at a lower torque, we get a higher speed. Okay, now do we in fact get a lower torque? I'm sure we do. Look, we have the equation KKF, and we can calculate it twice. One for case one, one for case two, and I do that here. Look at this case one, because now I have the KKF number. Case one, I get 53.1 Newton meters. And in case two, I get 8.5 Newton meters. 8.5. And yes, it follows the trend of high speed, low torque, low speed, high torque. Good. So I hope this example kind of hits home and brings all the equations together for a series motor. Okay, let's look at the next motor. So the next motor is a shunt or parallel wound motor. And it's parallel because now look at this, the field coils are in parallel with the armature as opposed to series. Your field coils are represented by this. Technically, there's an inductor here, but we're not drawing it because the voltage across an inductor in steady state is 0. Okay, so notice the difference here. Now IA and IF are not the same. You have a IL, which branches off by KCl into IF and IA. So you have some difference in this current, all right? What we're going to see, interestingly enough, is that the torque speed equation is the same. It's going to be nearly the same as the torque speed for a separately excited series. It looks like this, where it curves down. But for this one, it's actually the same linear slope. Okay, so the question asks, derive the torque speed relationship for a shunt DC motor. Well, like I said before, these two equations are still valid. Torque developed equals K phi IA, and Faraday's law, EA equals K phi omega M. Those are still valid. Also, Ampere's law is still valid. Phi equals KFIF. That doesn't change. So these physical fundamentals don't change. What does change is that IF and IA are no longer the same like in the series, okay? Does the Nodal Ohms Law still change? Well, is it still maintained? It is depending on where you look. Here, IA equals the node voltage here, VT minus EA over RA. That is correct, right? And we can plug in the EA into here, into this, okay, no problem. And we can do the same thing where we take this IA and plug it back into here. Good, right? And so again, look at this. We get the same thing as before. Torque developed equals minus K phi squared over RA times omega M plus K phi VT over RA. That is the same equation as a separately excited, and you're still going to get that, look, negative slope, linearly sloping down line. Now, if we dig a little deeper, the phi is proportional to IF, right? Just like in the series, the phi is also proportional to IF. And if we plug that in, let's see what happens. So what do we know? We know that we have another Nodal Ohms law over here, and that's written here. It's VT minus 0 over RF plus RA because these are in series. And I should write that down, actually. So this is minus 0, and this is in series, right? Just so that we can see our steps. I could take that and plug it in here, and that means this phi will pop into these 2 points, okay? And so that I know it kind of makes this a little bit nasty, this equation. But what do we have? Minus K phi VT squared over this squared, okay? And then you have KKF VT squared over RF plus R adjust here, okay? If you wanted to calculate the stall torque, well, or the torque at 0 speed, this term goes away. It's essentially the y-intercept. It's this guy here, KKF VT squared over RF plus RA plus times RF plus R adjust. That's this guy. If I want to calculate the no load speed, I can set the torque to 0 and then solve for this. Well, a lot of things cancel and you're left with this, okay? And so what's the consequence of that? Well, you get this equation here where the no load speed is this point. And if I look closely, this is the stall torque, which is here, okay? Notice if I increase V, it's actually rotating as opposed to translating. If you increase VT on the separately excited, you would actually translate the entire curve. Whereas here, notice it's not just, it's actually dependent on a square and it's rotating the whole curve. It's not changing the no load speed. The same is true for changing RA. Notice RA does not affect the no load speed. So decreasing RA will also rotate it, but it's not as sensitive as changing the voltage, okay? The other thing that you can notice is RF plus R adjust, which is controlling the field current, is rotating still, but it's also moving out the Y and X intercept, right? Because it's occurring in the no load speed as well as the stall torque, okay? So yes, the shape is still a linear negative slope line, but the parameters affect the behavior differently than in a separately excited, as it should, because it is physically a different system. Okay. All right. Let's do one more example, and then we'll call it for the lecture. Okay, so here's a shunt connected DC motor, same thing we just talked about, and then they give us some parameters. So they say that the current is 1.2 amps going through here. The RF plus R adjust is 400 ohms. The RA is 0.5 amps. The voltage here is 200 volts. And the speed here is operating at 1,150 RPM. So it's spinning, okay? Now, one interesting thing, piece of information they give is that the output power is 0 watts, right? So there's no external load on this system, right? No torque out on it. And the question is, what is the rotational power? Because you can imagine what's happening is you're applying some voltage, the energy is being burned off as heat, and it's being burned off in friction in the bearings, right? But it's not going into any output power, right? So it's just like the motor is just running without any spinning anything, right? So no load, okay? So the question is, well, how much energy is being burned off just in the bearings and the friction and the windage and all that stuff, okay? Well, one equation where the energy of the rotational losses showed up is the energy balance. So the input power minus the resistive electrical losses minus the rotational power equals the output power. And we're saying the problem is claiming that this is 0. So if we can calculate these two things, we can solve for this one. All right, well, let's look at the input power. We can just take IL times VT, is that right? Good, we have IL, we have VT, so that's a known quantity. The resistive losses, what do we have? We have IA squared times RA, and we have IF squared times RF plus R adjust. Do we know either of those? No. What's another equation for power for this guy? Well, this equation for power would also be VT squared over RF plus R adjust. Do we know VT? Yep. Do we know RF plus R adjust? Yep. Okay, so that's solved. But then what about this one? Could we solve for this current here? Let's see, what would be a way to solve for that current here? We know this load current, and we know that if we have this voltage and resistance here, we could solve for this current, in fact, IF, right, using an Ohms law or a Nodal Ohms law. And then once we have these two currents, we could solve for this current here using a KCL. And then once we have this current, we can do an I squared R here, okay? And so you can see this is kind of what we're getting at. Good. So you can see here's the things I plugged in. So this is your input power. These are your electrical losses. And this is solving for, yep, exactly, IF, solve for the IF. You have a KCL here. Sorry for a little bit of a mess here, KCL. You have that here, solve for IA. Once you have the IA, plug it in and you get the rotational power, 139.8 watts. The number really doesn't matter here. It's the intuition behind what's going on, okay? All right, this concludes the lecture for today, and I hope that helps. Okay, I'll see you in class.